Okay, welcome back after a long, well-deserved coffee break. So we have one more talk here before we go down and do the hands-on tutorials. This is Steen Lysgaard from the Department of Energy Conversion at Technical University of Denmark, and he will be talking about the Atomic Simulation Environment and genetic algorithms. Please.
Yes, thank you, Christian. So this is just the outline of what I'm going to talk about before we go down to the computer labs and have the tutorial about the genetic algorithm. So I'll just introduce genetic algorithms and some use they have, how they have been used in material science. I'll show some examples that we've been doing, mostly with these alloy nanoparticles. And also how lately we have begun to combine machine learning with the genetic algorithm. And we have done many things, and there are many more examples of what we have used genetic algorithms for on the Atomic Simulation Environment website. For example, we have looked at bulk systems for ammonia storage, or other people have looked at how to optimize the structure of particles on the supports. And I'll also give a advertisement of the Atomic Simulation Environment. And then I'll introduce the tutorial we're going to do, which is going to be about, we invested binary alloy slabs, which is, I know we have looked at many times before here, but it's just a nice test system, and I promise you the genetic algorithm will be used for many other things, just alloy slabs. So the idea behind genetic algorithm is very simple. It's based on natural selection. So I'll just go through this scheme here. You start by creating a random population of atomic structures. It can be candidates to the solution to your problem. You evaluate the candidates, and so in our case it could be you relax structures with DFT, and then while you evaluate, you determine the fitness of your population. Now the fitness can be any is the metric that you want to optimize. So that could be stability or band gap or any property that you wish to optimize in your phase space. And then the part where when one sets up a genetic algorithm, one has to do the most work is when you create new candidates, new structures based on your existing population. So normally one goes by that by crossover operations and mutations. And I'll come back to what those entail. Structures in your population that are selected based on their fitness. So they are selected to create new candidates, and then the idea is that the population evolve in this manner. You say you are converged when the population really stagnates, nothing happens for a lot of these situations. Now, this is a very simple outline. One can, as in anything, when one wants to use the genetic algorithm to the most efficiently, one has to customize it to the problem that you're looking at. So it can be really, you can add any level of complexity to it, so that your flow diagram can be quite hard to understand. I'll come a little bit back to the things just mention the previous work with genetic algorithms in material science. This is mostly revolved around two areas, nanoparticles, nanoalloys, and the prediction of crystal structures for any given composition. So this work on nanoparticles, nanoalloys really started or evolved quickly from 95 when this paper came out by Even and Ho, where they showed that they could predict this C60 molecule, the fluorine, using a genetic algorithm, and they introduced some new operators that hadn't been used before, and they represented the particle in real space instead of using a genetic encoding. So that, for example, when you do a crossover operation, and it can be performed on coordinates in real space, so that you are more likely to transfer the favorable traits of the parent to the offspring. And they also introduced geometrical relaxation of each new offspring, so that you really don't move blindly on the potential energy surface. You move on local minima all the time. That's what the geometrical relaxation takes care of. And around 2006, there was a lot of work done on predicting up to then unknown crystal structures from any given composition, also by just giving the composition, and then these people developed methods to operate on the atoms and on the unit cell vectors, so that they can predict the correct crystal structure for just an unknown composition. So just when is it beneficial to use a genetic algorithm? You really have to, since it's a non-deterministic method, so when you run it, you are actually not sure that when it emerges that you get the global optimum. So you really need some problem that you can't solve by just screening everything. Then it can be very beneficial to suggest what you need to calculate, and it can be used also for structural prediction. It's good for these corrugated energy landscapes with big energy barriers between local minima. You can do geometrical relaxation, it's no problem. And I say again, you can really optimize any barrier or any parameter, not just the energy or the stability. So I'll show some work we did a couple years ago on copper and nickel nanoparticles. The idea was to use these for CO2 reduction. So here we make an initial population of just random particles. We evaluate that. Here we have a fixed composition, so we just take the energy as the fitness. The operators we use are this cut splice, so you cut the particle in two via a plane, and then you splice together two parts of different variants, and then that involves the population. So we also introduced some customized mutation operators that was supposed to allow the algorithm to look at the special situations for these particles. For example, you switch atomic identity of atoms in the core particle with one in the shell that could create these core shell particles, or you could move atoms from regions where there's no of its own type of neighbors to a region that has a lot of it, and the other way around. That's to create mixing of or segregation. So when you run this algorithm, you can see this is just an illustration of how the lowest energy we have in our population goes down as we run the generations. So we start out just by having a more or less random particle. It goes down in energy, and at some point this geometrical normalization takes care of changing the structure from cuboid-tetrahedral to an icosahedral structure, which is lower energy. And then the ordering of the atoms takes the rest of the time, so that all the copper is at the surface and the nickel is in the core. What we learned from this also was when we tried to vary the number of times we did mutations. So normally when you do an operation on a particle, you do the mutation once and then feed it back into the population, see if it has evolved. Here we try to actually do it once, but also try to do things 5 times, 10 times, 20 times. So do a more rough operation on it. And not surprisingly, it turned out that doing more operation was more beneficial in the beginning, but after a while, the population is that well converged that nothing will get through, nothing will go into the population since you're doing such a too drastic mutation. So the one where we only did one mutation actually turns out to give the lowest energy. But the conclusion of this is that it is beneficial to have like a dynamic operator that works does more here in the beginning and then does less as you start to converge your population. Now, in this example, we looked at again copper gold particles, also for use in CO2 reduction. And here we don't keep any constraints on the composition. So we want to really determine the full complex hull. So in order to do that, we need to use this mixing energy as the fitness parameter. In that sense, we use the energy of a mixed particle and subtract the chemical potential, which we define from just a pure particle. Now these are highly symmetric particles, so we first did like a screening of all. So you substitute all atoms in the shell of this particle with the other type, and then you do all combinations of that on all the shells in the particle. And you get all these points, and the convex hull defined by the red line. So let's zoom into the bottom region there, where we've got the genetic algorithm running, where the lighter the points, the circles, that's the later in the algorithm. So you can see it starts here, and all the points here are in the end of the algorithm. You can actually see that some of them are below the convex hull defined by this screening we did. So it actually turned out the algorithm found particle to have to be the global minimum that wasn't symmetric. So it has a copper core with a few gold atoms in there with only copper neighbors, and on the surface there's actually copper on the terraces. So this is most likely to relieve some of the strain that's in these particles. But it's hard to explain why exactly there should be this number of copper on the terraces on the surface here. So this we tried this. The whole reason for doing this study was to see if we could break the scaling relation between COH and CO on using such a particle. We heard about yesterday this activity volcano for catalytic reaction, where you can define the activity by two descriptors, which is the CO binding energy and the COH. But unfortunately for pure metals, these two energies they scale, so you can't really cross this line if you just use pure metals. And apparently for this particle, the binding energies also did not prove this line that came from extended surfaces. So that was a shame, but it was a nice example. Oops. So this last example, we tried a little smaller particle, 147 atoms, and again we wanted to determine the complex salt. So one way was to just fix the composition and run the genetic algorithm and do that for each composition. So in order to determine the complex salt, here's plotted how many energy evaluations is needed per, and this down here is the composition between platinum and gold. And you can see it's between 1,000 and 10,000 evaluations for just doing it the simple way. Now, if you use a population where you have all of your particles in one population, but you level them so that the best one in each composition will have an equal likelihood of being selected for appropriation, then we're able to get down to approximately 100 per composition in order to determine this complex salt. If we add another part to the algorithm, so we now use a fingerprint, as we heard about earlier today. We use the fingerprint of how many years neighbors does each type of atom has on average. That works well here, and if we don't allow more than one of each fingerprint and each composition in the population, then we are able to go a little bit further down in the number of energy evaluations needed. Now, if we use, we can add some machine learning here to propose or to check if the particle that is comes from the algorithm. We use some machine learning to predict if that is going to be included in the population, and if not, then we don't bother doing the expensive energy evaluation. So if we do that, then we're able to get further down. And if you use a genetic algorithm with an operator that's basically another genetic algorithm that has the machine learning part as an operator, or that as an energy evaluation, and then you run this just by letting the machine evaluate energy, and then come up with new structures for the GA, and you're able to get down to much more than 10 energy evaluations per composition. So we can just see here some summary numbers of that. So here we plotted the convex hull for the 5 different types of genetic algorithms we ran. And we're able to go from approximately 500,000 energy evaluations needed to not much more than 1,000. So that's quite encouraging, and we'll try to use some of these methods in the tutorial that we're going to do later. Okay, so I promised to just do a little advertisement of this atomic simulation environment that we use, and where you are going to use in the tutorial, and the genetic algorithms implemented in it as well. So this is a Python library for working with atoms. So atoms object is really the central part of all you do here. So there's a lot of modules in this library. One of the important things, of course, you can have a electronic structure calculator and just attach this object to your atoms and calculate energy. Write that line in Python, and it will give you back the energy. You can do much more things like geometry optimization. You can do NED calculations, molecular dynamics. You can put constraints on your atoms. So you can fix atoms in the slab. The way you read in atoms, you can either have files you download from the web, or there's a lot of utility functions that can build structures for you. So all in all, it's a great package. This started development back in 2002, but this year the recent review of everything that's in the Atomic Simulation Environment came out, because it was about time. There was so much new stuff that was there. So in this paper you can read all about it. And there was a lot of contributors, so all these have contributed with code for the package in some way. This is just a small example of how easy it is to set up a calculation. As I said, the atoms object is the central part. The calculator object is your electronic structure code. This is Northwestern Chem. Optimizer, you can use different algorithms to optimize your atoms. And you can also write out atoms. So here we set up an atom subject with some atoms in it. We set up the calculator object, and we run a geometrical relaxation and get the potential energy. So this is very simple things to work with. And you get all the advantages of using Python on top of that. We'll see more in the tutorial. This is all the calculators that is supported. So both differential, but also all electrical codes that should have come before. So let me say a little intro to the tutorial. We're going to determine again the convex hull, defining our slab using the GA. And if you want a real use for this, we can perhaps use this to try to break the scaling relations between atomic energies, as I talked about before. So the number of combinations for such a slab here, 24 atoms, are 16 million, so without taking into account the symmetry. So we can't really do brute force search. We need something better than that. That's why we use the algorithm in this case. So we use this. We will use this population where we level all the compositions. So instead of having energy or a ranking like this, where a certain composition has all the lowest energies, so a traditional algorithm would just use these as the population and involve really only this part of the composition space. We now take each composition individually and rank them so they are equally likely to be chosen as parents for the next population. So this works well because there's a lot of similar chemical ordering between neighboring compositions, and you don't have to invent a good composition or good ordering for each composition. We use the type of operators as I also described before, cut and splice, and limitations and substitution of atoms. We will try to implement some way of detecting whether we have, when the algorithm proposes a new structure, we will try to detect if we have performed a calculation on a similar candidate before, because that's just that's a way to avoid doing duplicate calculation, and also a way to have a diverse population to avoid premature convergence of the algorithm. And so in the end, we should most likely get something this for this copper platinum example that I've chosen. So that's really it. And you have to go to this website as yesterday to get started. There should be instructions there. Yeah, and that's really it. Thanks for the attention.